Good morning, good evening, good afternoon, depending on where you are in the world. Thank you for joining us today for today's CNCF webinar, MLOps operation with Git-based CICD for ML. I'm Christy Tan. I'll be moderating today's webinar. We would like to welcome our presenter today, Yaron Haviv, co-founder and CTO of Iguazio. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there and we'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinars page at cncf.io/webinars. With that, I'll hand it over to Yaron to kick off today's presentation. Take it away.
Thank you. And hi, everyone. I'm Yaron. I'm the co-founder and CTO of Iguazio. Iguazio is a very early member of CNCF, and we've been active in a variety of areas. What we're going to speak about today is sort of CI/CD and DevOps for machine learning. What are the unique characteristics, what you can do in order to, again, bring agility of DevOps and MLOps into your machine learning initiatives, and obviously leveraging CNCF tools like Kubernetes and others. And with that, I'll just start with the presentation. And again, the slides will be available later, and you can ping me in LinkedIn or Slack, Kubernetes, or CNCF Slack, and in both places. So first, before we dive into the solution and what we're trying to solve, let's talk about the problem. The main problem today in machine learning is that once you've finalized the research and you develop something in small scale, you extracted some data, you ran some exploratory data analysis, machine learning again in small scale in your notebook, and evaluation, you feel you're ready, and now you need to create something that runs in production. The production implementation usually is a re-implementation. It uses different frameworks. It's designed for scale. It's designed to be always on. It needs to be observed, and all those things that signify a sort of a production environment. If you look at the diagram on the right, you see that we need to feed data from real data sources, from production data sources, from streaming data. We end up with very large scale data. So you have to analyze it in a distributed fashion, not within our notebook. Later on, we need to run training, and this training may run in sort of a CI manner, in an automated fashion every time a data changes or every time we change code or logic or models. And finally, we need to serve the models as well as monitor them. And serving a model requires also having real-time data that is exactly the same like the training data, just runs faster in a more interactive way. So usually when people build those solutions, they re-implement. In some cases, they use Hadoop and Spark and streaming technologies. In some cases, they leverage Kubernetes. Sometimes they change the code from Python to Java or rewrite the code to make it more hardened, take into consideration security and other aspects. One of the main challenges in that transition is that when data scientists implement code, they write it usually in sort of notebooks. A data scientist focuses not on coding, they're not developers, they're data scientists, so their focus is on the best mathematics, the best statistics algorithms, the best deep learning or neural networks, and not necessarily on making their code robust, making their code deployable, scalable, and all those things that as a software developer or a DevOps person you usually care about. So the main challenge is, how do you take code that wasn't designed for anything operational? Usually, if you look at a notebook, it's not even divided to functional building blocks. You have the same notebook with training, with data preparation, with charting, with sort of inferencing, everything in one jumbo notebook. And at the end, in order to run it in production, we have to turn it into a set of microservices that will run on a cluster in a real-time or batch pipeline. So that's the main challenge that we need to solve before thinking about how to operationalize or automate our data science pipelines. So just looking into the various steps in productizing any artifact, data engineering, data science, or even traditional software, but when you're dealing with data, there are bigger challenges, especially around data parallelization and performance and others. So if we take our code, the first step that we need to do is package it in Docker and have scripts and make and command lines and all of that. And you think it's trivial, but for a data scientist, it's probably not trivial. So we need to, sometimes someone else will take the code and convert it into a Dockerized, containerized workload. And then you need to think about scaling out. And scaling out when you're dealing with data requires various aspects, not just load balancing or service meshes. Sometimes you have to partition the data. You have to partition your model, distribute it, maybe run AutoML or hyperparameter tuning, which is running various permutations with the same logic and different parameters. Finally, when you've done that, you need to think about performance. Data code that was written for research usually doesn't have low latency, doesn't have high throughput. And someone needs to start thinking about, you know what, maybe I need to cache queries. Maybe I need to introduce GPUs, add parallelism, make it asynchronous instead of synchronous, etc. And all those things require engineering efforts, require developers that do this engineering. They could be developers, they could be data engineers, depending on the organization. Sometimes they're called ML engineers. Once we have the performance sorted and ready, then we need to think about all the instrumentation aspects, monitoring, logging, instrument observability, versioning, security. Now, this goes beyond the traditional microservices and cloud native architecture, because we're not just monitoring the container. We have to log and monitor the data. We have to monitor the versioning of the data. We have to apply security also for data access. So this is more complicated, especially when there is liability associated with machine learning. If our model doesn't predict things properly, we may lose money. We may annoy someone and he wants to sue us because we made some gender bias. So everything we do in the pipeline, our code, our data, our models, our algorithms, everything has to be versioned and controlled. And finally, we don't want to repeat the same thing over and over again, so we have to apply automation. Pretty much like we're doing with other cloud architectures, we need to apply CICD and automated workflows and rolling upgrades and canaries and A/B testing. The main challenge here is that once you have the prototype up and running, it may take a few weeks, because today machine learning is well understood. You just take an XGBoost model and you feed it with some data and you get a model. The main challenge today is that productizing the entire thing would take about 12 to 18 months from many organizations that I work with. So the main challenge is how to automate that and also break the silos between developers, data scientists, data engineers, and let them work on one ecosystem. So first, what is MLOps? So we understand what is DevOps. DevOps role is essentially to combine the development and operations and think together how they can accelerate the business, or how they can allow the business to deploy software faster in an operationalized manner. So MLOps is essentially similar, just extends it with a lot of data and machine learning practices of data engineering, again, building models, reliability, observability, all of those aspects. So let's take into account a use case. A simple use case would be predictive maintenance pipeline. So we can see that even in this pipeline, we have many different steps. The first steps is to essentially bring the data in. The data could come in different forms. It could come in streaming data, or just come from a variety of databases, operational databases, and we need to run some ETL. We take all that data and throw it into sort of a pile, usually sort of files in a file system. Later, we need to run some processing, some analysis to combine different data sets, to denormalize, to join, to aggregate, and form what we usually call a feature vector or a batch feature vector. That feature vector essentially have a denormalized set of all the features that we're going to train our model with. Once we have that feature set, we don't necessarily want all the features. So we have to do some feature analysis and feature detection and detect which features are the more meaningful. Maybe some of them should be dropped. Maybe some of them should be emphasized or changed or modified. And so we have to have another step of feature detection and processing. And then we have some data that we want to feed into our training logic. Usually we split the data into a training set and validation set, smaller validation set, and we run our logic and we measure the accuracy of our model. And finally, we generate the model along with some sort of reports to tell us how good is our model or maybe other aspects of our model. This is all just creating the model. What about running this in a more production environment? You have to deploy it in an online system. So you have to take this model and wrap it in a container. It's not just the model in a container. You also have to provide APIs that, for example, if I'm providing you a user ID and maybe an ad number or something like that, you have to enrich that data into a full-blown feature vector similar to the one that you've been using in the training, and only then pass it to the model. So this is real-time feature engineering aspect that needs to take data from the real data sources. After you've done your model serving, you have to track all the behavior of your model so you can identify if the model is misbehaving, if the accuracy is getting lost. All model is eventually lose accuracy. Sometimes also, due to the challenge of having the same data for training and serving, the models are in day one already inaccurate. Because if you're not giving the model, it's essentially a math equation. You won't give it the same data, it won't produce the same results. So anyway, we have to have a tracking system that monitors all the data, all the requests, all the responses of our model, and detect the behavior, the performance, the drift. And this can also be combined later on with real data. After we've made some prediction, after a while, we know if our prediction was correct or not. And we can analyze that with reference data and measure how well behaving is our model. In many cases, we actually don't serve a single model. We serve things called ensembles or other more complicated scenarios. And we can essentially say, you know what, this one has better performance. Let's prioritize that. Let's give it a bigger weight, etc. Or we may need to retrain the model and feed it with fresh data that increases our accuracy. So what you see here is a very complicated flow of delivering machine learning into production. The way that we see one of the ways to accelerate that is to essentially take those microservices and use the concept of serverless functions. Not necessarily the serverless functions that you guys think of sort of event-driven, but serverless functions that also know how to process data and could be stateful, etc. And because we can use those functions, we can even put them in a library and reuse functions and scale them out, because usually serverless engines know how to scale out workloads, etc. One of the challenges with integrating such a big solution is that you have to use many different tools for offline, for online, for data engineering, for machine learning, and you end up having some cloud provider tools and maybe something in Hadoop and something in Kubernetes and something on your desktop. And it's a big nightmare. It's a big nightmare to develop the security, and it's a big nightmare to make sure everything works and maintain multiple platforms. So we believe that Kubernetes should be a standard for all of those tools. So instead of having like a silo of Hadoop and some silos of SaaS services, etc., if we can put everything on Kubernetes and build an ecosystem around it, that could ease the deployment hassle. We can use the same security paradigms, the same API concepts, etc. So essentially, what do we want to do? We want to build a system where we can feed data from a variety of sources. We can run data preparation at scale on the same system, run accelerated training at scale, again, on the same system, and finally deploy the models as a set of microservices with APIs and feature engineering to go along with the deployment. and even monitoring services, all of that on the same platform. And also another thing that we need to take care of is sharing data across those variety of steps in a pipeline. So if we open up this pipeline and look into what is really built into that pipeline, so we have to have 3 layers in the solution. The first underlying layer is data. So we need we need the data to store all this information, intermediate information between one step and another. Sometimes this data is structured. Sometimes this data is unstructured. Sometimes it's tables, sometimes it's files. But the first step would essentially ingest data from a variety of sources. Again, ETL, streaming, logs, scraping. Then we are going to run microservices for data preparation. They will generate a subset of data. Finally, later on, we run training. When we're running training, we may want to run different microservices that run different algorithms in parallel, and then choose the best model that has the best algorithm. Sometimes it's referred to as AutoML, or there is also a notion of hyperparameter tuning where you can run many different permutations of the same model. You generate the model, you generate some results, then you do validation, and finally deployment. Now, one of the key things here is that if we can leverage the concept of serverless functions, we can very easily go and deploy some code, have fully automated flow of delivering the code, fully automated flow for instrumenting the code and scaling the code, etc. And on top, we need some orchestration framework for tracking and managing this workflow, and there are some solutions for that in the Kubernetes ecosystem, as I'm going to demonstrate. Okay, so let's look into the architecture of how we can deliver such a solution. So the first thing that we need to have is sort of a data layer. Data layer usually will comprise of 2 types of data. One is sort of structured, high-performance data in the form of sort of a database or a high-speed shared file system. The second thing will be sort of where you put your blobs and your large-scale storage, data warehouses, different cloud services that serve object or files or databases. On top of it, we need to have a cluster with all those shared resources. So Kubernetes is the ideal environment for that. On top of it, there are many different services that comprise this ecosystem or this pipeline that I just showed, require all those separate tools, things for deep learning like TensorFlow and PyTorch, services for data analysis like Spark or Presto or Dask, services for training like Orvod, etc. We need to put all of those in one framework. And we could also use other serverless frameworks like Nucleo in order to do things like service and real-time serving, real-time ingestion, stream processing, etc. On top of it, we need to have a set of higher-level tools for AutoML, for example, to automate this workflow of training, to automate this workflow of feature selection. Also, we need to have sort of experiment and run execution tracking. So everything that we do has to be tracked automatically. We don't want to have manual work around it. We want to have a feature store. A feature store is a concept where all those features that we're going to produce and consume are managed in one sort of a place, including all the automation and recipes of how to produce those. And finally, we need a workflow engine. One of the best workflow engines on top of Kubernetes is something called Argo, and that has a flavor that's suited for machine learning and data science, which is called Kubeflow or Kubeflow pipelines. And obviously, we want to integrate all of that with source control like Git. Okay, so looking at my, another thing that we discussed is use of serverless functions in order to accelerate all this flow of developing the code, making it a container, running the scalability, accelerating the performance, doing the instrumentation, and also all the CI aspects of that. So what we want to do is, again, automate the code to production flow. The other things that we mentioned, that many of those use cases require large scale processing. So we need elastic scaling of those processing, and sometimes maybe scale to zero because we don't want to consume GPUs and CPUs if our workloads are not really working. We mentioned having to do logging and monitoring. If we can leverage that freely, why not? And there is another point that usually if people think of serverless as something which is slower. The solutions that we developed in our open source, like Nucleo and MLRun and others, are essentially designed to accelerate your performance because they bring in a lot of techniques from high performance computing and real-time processing. And for example, with Nucleo, you see here a sample of a benchmark running the same data processing function. There is a blog on that in Towards Data Science. The same data processing function running as a simple container with Python runs about 20 megabytes per second, and running the same code exactly without modifying a single line would run about 500 megabytes per second on a Nucleo function controller. And that's because it knows how to create parallelism for Python. It knows how to handle memory and GPUs in a much more efficient way than the traditional things that wrap your code. Another thing that once you've done that, we have a building blocks that people can publish and other people can consume and build a workflow out of it. And you can also serve a marketplace. So people can just drag functions, place them in a pipeline, run this entire pipeline, and maybe even use functions that are pre-built, like AutoML functions and deployment functions that I'm going to demonstrate. One of the things that when we think about serverless, we usually think about event-driven processing, like Amazon Lambda or Knative or things like that. Now, the point is that if you're running machine learning or data engineering, there are different requirements. In serverless, typically it's event-driven, short-lived, stateless workloads. But when we're processing data, we need other things. We need jobs that may run for half an hour. We need to distribute the workload instead of just using an ingress or a load balancer or service mesh. We have to think about the data. So we need to apply things like data partitioning, data shuffling, reduction barriers, hyperparameter exchange, other techniques that allow us to create parallelism for more sophisticated workloads. And we have to have state. Workloads with data obviously are stateful. And the way that we pass data along the pipeline, or the way we pass data between one step and another, requires passing not JSON events, but rather a complete data set or a set of parameters. So we have to build a new thing that is like serverless in the notion that it's has the built-in elasticity, it has all the automation around deployment and operation, but works with other frameworks. So for that, one of the things that we've developed is in a package, is part of a package called MLRun, which is a full end-to-end MLOps orchestration layer. There is also a portion that automates the creation of CRDs and treats a variety of CRDs in Kubernetes as serverless functions. So essentially it knows how to orchestrate not only event-driven workloads, but things that handle deep learning like Horvath, or it knows how to orchestrate Spark or Presto as serverless functions. Though I can essentially run a Spark job as if it was just a function, or run a distributed deep learning logic as if it was a function. But the trick and the way that it works is essentially allowing you to scale out the containers, but also provision low latency messaging across those containers and data exchange across those containers using a low latency data fabric. And this way you can scale dynamically the workload, even for very intensive jobs. It also sandbox all your workload and monitors everything that goes in and out, so you automatically get all the experiment tracking, all the job tracking, as I'm going to show in a demo in a minute. So what you gain is scale and performance without the hassle. It also, because it knows how to create a lot of parallelism, instead of having a separate system for AutoML or hyperparameters like Knative or others that you need to integrate manually, essentially MLRun also does AutoML and hyperparameters, so it knows how to distribute workloads and distribute parameters and also exchange algorithms in order to create parallelism for the entire training and analysis phases. And again, it has a variety of CRDs that it controls, and this list is going to grow bigger because it's just essentially through plug-in mechanisms. The other very critical part in the solution is a workflow processing engine. So this is where Argo comes in. It's an engine on top of Kubernetes that knows how to enforce a state machine. And there is a project called Kubeflow and Kubeflow Pipeline that essentially builds a machine learning pipeline on top of this Argo. What is Kubeflow? Kubeflow is a project that has several sub-projects within it. Pipeline is this machine learning orchestration. It also has a managed notebooks, and it has CRDs specific to machine learning workloads like distributed TensorFlow, distributed XGBoost, and PyTorch, etc. What we've done, we've taken those components from Kubeflow and we wrapped them in sort of more of a serverless and fully automated frameworks like MLRun and Nucleo and others. And so what it allows you, again, to publish code into microservices without doing almost anything. It provides a glueless data access and parallelism that I mentioned. It allows you to run steps within Kubeflow which are distributed. Usually in Kubeflow, you'll run it one step at a time. Every step is a container. We now extended it to a notion that every step in a pipeline could actually span 20 containers and also have GPU acceleration built into it. And everything is tracked automatically. Code, execution, data, versioning, everything is auto-tracked through some sandboxing technology built into it. Now let's think about the entire flow and start seeing how we involve Git and more automated workflows. One of the challenges of something like Kubeflow is that when you have to run everything on Kubernetes on a distributed pipeline. But that's not really how data scientists work. Data scientists want to work off their notebook and start doing some experiments. And then they want to run a single microservice that, for example, does the training or does some data preparation. And finally, you want to build a bigger workflow that combines all the individual steps. So we have to think also about the data scientists as first-class citizens. Usually the concept around Kubernetes and Kubeflow and those tools is that DevOps or developers are the first-class citizens. So we have to sort of flip this around and provide something which is very intuitive, very familiar to data scientists. So one of the things that we have here is an SDK that they can use inside their IDE, Jupyter, PyCharm, VS Code, etc. And then they run everything within their native environment as if it's just, they can track every experiment, they can track every run, etc. At a certain point, they want to have bigger amount of resources run on real data that's part of a cluster. So what they can do from within their notebooks, within their environment, they just push one command or one API call. And essentially what it does, it wraps their entire code. It ships it into the Kubernetes cluster for an API gateway. It builds the containers based on the requirements and dependencies and all of that, and runs it as a distributed job on the cluster and tracks all the behavior as if it's running in the native environment. I'll show you in a minute. You actually see the console of the Kubernetes job in the Jupyter notebook of the client. So again, gives them the familiar environment. They don't need to understand what Kubernetes is. They just know that their code now runs distributed on a massive cluster. And when job is going to end, all the resources are going to get decommissioned, including GPUs, CPUs, memory. So that means that we can have a shared cluster for all of those resources. Now we're cozy, we've built a function, we see that it works, whether it's a training function or data preparation function, and we now want to run it as a part of a complete workflow. So we have individual functions, as we've seen before, one for data gathering, one for training, one for validation, deployment functions, etc. Now someone else, an ML engineer or a DevOps engineer, may just grab those individual functions, stitch them into a pipeline, and run this entire pipeline as a complete workflow, whether it's a production pipeline or training pipeline or development pipeline, etc. Now, instead of running it interactively, we can actually have exactly the same flow run in a Git pull request. So when someone is pushing code, we can make this pipeline, grab all the code, all the components, the data, the functions, the different metadata, and convert it into a Kubeflow pipeline, run it distributed on the entire cluster, track everything as if it was in a bunch of individual runs. And eventually, if we want, it can actually throw in a Slack notification with a summary and also write back into our pull request, write back the results of the training. And someone can just look at the pull request and say, you know what, I feel good about this model. Let's promote it into production with a single command line inside the pull request. So this is the flow. Again, it's very advanced flow. I'm sure not everyone is going to jump into it immediately. The customers that we have that have jumped into this sort of workflow see much higher productivity. They can deploy new models. They can do updates frequently because everything is sort of very cloud native and very automated. So again, looking into this flow of development, CI and CD, let's look at it again from a more of a complete workflow. Let's assume we have a Git repository. This Git repository, we just take a branch. We want to build something, let's say a training function or a data preparation or analysis function. We can write it inside our notebook and test it. We see that it's working great. We just push one command, convert it into a microservice. And then once it's a microservice, we want to see that it's actually working on the cluster. We haven't missed some dependencies, or there's no issue with the scale out frameworks or whatever. If it breaks, we go back to development. Once we feel it's ready, we move to a CI phase. So we create a pull request. There's automation frameworks that examine our Python code for code inspection, maybe visual review. When we feel this is ready, we want to run the pipeline. We don't necessarily want to run the pipeline immediately because machine learning pipelines are expensive. They may use GPUs and other things. So we want to run initially some unit testing and then run the entire pipeline. We can do that from a pull request, as I'm going to demonstrate. And finally, if it's all passed and everything is great, we merge that pull request. We may have additional tests on our sort of development branch before we release a version. At a certain point, we feel cozy about that and we want to create a new version. We promote our code into some master branch, depending on your development paradigm. We tag the version with some label. We deploy that in a canary, and we could even put, when we're tagging, we can even automate the deployment as the minute that we're doing a tag. Once we're running the canary and we see that the canary is working properly for some while, canary is essentially putting some percentage of the workload on some microservices or on the new ones, and most of it will go to the old microservices. Once it's ready, we promote it, and then we need continuous development and continuous monitoring for concept drifts, for accuracy, disruptions, etc. And if something breaks, we can roll back to older models, or we can go and retrain our model and run this flow again. So this is a complete workflow of automated machine learning. So one example of one of the customers that we have, there's a nice use case around it, is working with traditionally with Hadoop, running a SQL server and doing ETLs periodically, and then sort of using some R server to do the prediction. Because everything is very batch oriented and very Hadoop, so it has two downsides. One is extremely complicated, a lot of engineering efforts to make sure that everything works. The second is extremely slow because it's batch processing. So what they moved into more of a real-time workflow or continuous workflow based on microservices, where they ingest the data directly from the database on every database transaction change. Then they run the analysis of those features in real time using serverless functions. They throw in the analyzed data into an online offline feature store. They may run additional batch analysis periodically to look at the bigger view, a longer time view. Every a certain amount of time, they would run model training as a microservice using scikit-learn that essentially generates a new model, extracts a feature set, generates a new model, and there's a model inferencing function that essentially get trigger events from a stream, analyze the results, the feature vector, and immediately block the transaction on the fraudulent account. So it pushes back into the user database an update on the user if it's a fraud transaction to block the account. And that workflow, instead of having like 40 minutes because it's batch, is now a continuous workflow that 12 seconds from the first indication of fraud, it already blocked the account. Everything is fresh data, everything is online, everything is microservices. Another side effect of that thing is that you can actually roll new versions for each individual components. You know, microservices is about breaking the monolith to individual small components. So every time we want to change something, change our model, change our analysis, etc., we just do a rolling upgrade, and a week from now we can release a new version. So moving from a cadence of 3-4 months for release, we move into a weekly cadence of versions. Worst case, something doesn't work well, we just roll back to the previous version. Nothing happened. So with that, I'm going to show you a demo, and to show that all this nice vision is also working in practice. So okay, so let's look at some notebooks, and let's start with a simple notebook just to explain what is a function and how to work with those functions, and later on we'll show how to apply automation and full CI into the same thing. So what we said is that we want to be sort of friendly with the data scientist. So we want to let them develop in their native environment. So their native environment would be like a Python, you know, notebook. So let's assume I want to build a simple function that essentially opens some archives, some, you know, S3 bucket, and load some zip with images, and then I'm going to do a variety of things with those images. So I want to write a simple Python function, get some archive URL, generates results, you know, unzip it into a target location. It's a good practice to document my function. This documentation, by the way, is going to be auto-learned, and I'm going to show you in a minute. And I'm just going to write my code. Another thing that we want to pass to this function is context. Context is something that allows us to log artifacts, to do instrumentation, monitoring, metering, pass secrets into our function in a sort of a very secure way. So this function is relatively simple. And in order to make it a microservice, we only do a single operation. We just say, take our code, make it a function. We can even document our function, you see, give it categories and description and other things, because this function is also going to be cataloged. So once it's cataloged, we can actually drag it and run it without even opening an editor. And it's actually also a resource. You know, if you're going to look into that function as a YAML, you'll see that it's sort of like a Kubernetes resource. And then I can just export it or save it in a database, upload it to a marketplace. At a certain point, I want to read this function from a repository or from a marketplace. I want to examine its documentation. So you see, it suddenly has documentation, and this documentation arrived from my own documentation. So I didn't even have to do anything special. It parsed my Python code, extracted my documentation, and then I just want to run this function. I'm giving it sort of a task, is a set of parameters and input data, and I want to run it initially in my notebook. I don't want to run it on the cluster, so I can just say run local. It will run it on my notebook, and I can see the results, I can see the logs, everything is great. At a certain point, I want to run it on the cluster. So I just choose a different command, and you'll see that essentially it's allocating a pod or multiple pods if it's a distributed job. And I see this exact same logs as if it was running in my own notebook. Just this time it was running on the cluster distributed. And I can do other things with it. By the way, I can even go back into the ML Run UI. So everything that I did is also logged into a database. So I can see this function that I was running, what it generated, you know, the results, the logs, see the same logs that I've seen here. And I maybe just want to run a job from here, you know, And you see all the parameters that I documented in my code are actually just parameters that I can just click and type. You know, maybe I want to give other resources to that function, you know, GPUs, CPUs, etc., and run it now or in a schedule. So someone can develop in his notebook and just pass it into something that someone else can operationalize extremely easy. Now, the next thing that we want to do is build a complete pipeline and full automation. So let's take another project. This project is also documented in here. I'll send the links in a minute so people can look into that. This is for the MLRun repo, and there are other repos there that you'll see with this full demo of how to do fully automated CI/CD. So let's go back into our notebook. This time is a more of a real use case. So we can start with a single function, the simple function that generates data. This is generating the iris data set. It's a common data set in machine learning. This function of ours also wants to log the data set into the artifact repository. So what it will do, it will essentially log it into sort of a metadata service that stores features and other things. By the way, by logging it, it also already analyzes it, and you'll see all the statistics and all the behavior of that data set in the UI automatically. And we can do other things with that. So we just generated the data, and later on, we want to run it. We can form a notion of a project, because sometimes we want to take all those functions and to put them in one project. Let's say our HR analysis, our fraud detection project, whatever. So we're just going to run this data analysis or this data ingestion function, and it will analyze our data. It will show all the results. We get a hyperlink into the UI if you want to see it in a more visual way. The next thing that we want to do is run analysis on our data. So this time I'm going to take a library function, which is a feature analysis function. It essentially takes the data set that I just generated, and it will analyze it to verify, to generate plots around it. So as a data scientist, I don't need to work hard on packaging containers and distributed workloads. I'm just going to run a distributed data analysis on my code. So I'm just going to grab a function from a marketplace, see the documentation. You know, it has a bunch of interesting parameters. I'm just going to run it on my cluster. One of the things that we can do is put modifiers. It's a concept of Kubeflow, of essentially adding things like resources like volumes and other things. So here I want to attach, because I want this analysis function to see the data on my notebook, I need both of them to sit on a shared, fast shared file system. So I'm I'm essentially mounting both containers on the same file system, my Jupyter notebook and my analysis function. And this way you can see that I'm actually passing the output of my local notebook into that function. In reality, I'm not really moving any data, I'm just passing a pointer, because they're both running on a high-speed shared file system. And that could also be done with NFS, by the way. So I'm just running this analysis function, and you see that it's running as if it's running locally, but this job, again, is running on a separate pod on the same cluster, just sharing the data with my Jupyter notebook, and it generates a lot of data. Now, nice thing, because it's a shared file system, I can just see that in my notebook. So let's see what we generated. We've generated all sorts of feature analysis diagrams, billing charts, if you're familiar with that. And again, a variety of analysis charts for my data set. At a certain point, I want to build a full pipeline, not just analysis. Now I feel the data is ready. I chose the right features. So the next thing I'm going to do is, So the next thing I want to do is build the pipeline. So building the pipeline, again, I don't want to work too hard. I want to take AutoML training function. I want to run testing and validation function. I need to deploy my models, so I need a model serving function. And also, after deploying my model, I want to verify that it's actually performing well. So I need a model serving testing function that actually bombards my model serving HTTP endpoint with a set of data and verify the latency, the performance, the behavior of my model. So again, a full pipeline. So in order to run this pipeline, I use Kubeflow pipeline, which is again a standard on top of Kubernetes using Argo. And in that pipeline, I'm going to have a bunch of steps. The first step is ingesting data, running this function that I just defined in my notebook. Again, I take my notebook and I'm running it in a pipeline without building any container. That MLRun did all the magic for me. Then I'm running an analysis function that takes the output of my ingestion function. I'm running AutoML function on my data set using a set of algorithms that are more suitable for this type of data set. I'm asking it to automatically choose the best accuracy across all those permutations. Finally, I'm running validation against the results of my model. And when I have a model in my hand, I'm going to deploy that into the cluster. I'm just going to pass the model from the training into a new function that does deployment, giving it some parameters, and that will deploy a real-time microservice. So essentially, what we've done here, we've taken Kubeflow, which is usually a machine learning pipeline. We've extended it to do data analysis pipeline, data preparation pipeline, things that you usually do with like Airflow. And then we ran machine learning pipeline for training and validation. And finally, we're running a deployment pipeline, something that you would usually do with Jenkins or other CI tools. So we have a single pipeline that does data engineering, machine learning, and CI in a single flow. In order to run this thing, the only thing I need to do is just ask for run, and I can watch the results locally, so you can see that if I'm watching the results, I'm going to get all the results back into my notebook. I don't have to open the Kubeflow pipeline UI. But if we want to look into Kubeflow pipeline, this is integrated as a managed service in our Iguazu platform. Then you could just go and see this pipeline that I just defined. You see the first step was getting the data. Here's a snapshot of my data. A second step was training the data. Here are all the ROC curves. You see all the visualization, which is very hard usually to do in Kubeflow. All the visualization is automatically generated inside Kubeflow without doing any work on my container. I can run testing. I can run the analysis, as I've shown, of all those nice charts. I run the deployment, which is essentially generating a Nucleo real-time serverless function and generating a real-time endpoint. And finally, I'm running a testing a utility where I can see the latency. You see I'm roughly like 5 millisecond latency, which is relatively good for that model. So I know that my model behaves well. The point is that I don't want to run this manually, just as I've done right now. I want to run this entire thing in Git. So the way to do it, if you clone this repository and you install MLRun and Kubeflow on your Kubernetes cluster, you can follow all the documentation on how to do that. You can just write a GitHub Actions workflow, or just throw in this YAML. If you clone the repo, it's already there, which is essentially going to remote launch MLRun and Kubeflow every time there is a change or there is a commit in my repository. So what I can do, I can edit the code that is here in the repository. It's essentially the same project that I've just shown you. Part of every project, there's like a project YAML file, which is, tells us all the information about the linked functions and data and parameters, etc. Very simple and intuitive YAML file that is generated for you. You don't generate it. When you save a project, it generates that YAML. And then the way that it works is that you can just pull request your code. When you pull request, you do, in the pull request, I could just do /run. This will automatically trigger a workflow, remote workflow in Kubernetes, so in Kubeflow. So you see it generates a pipeline. Once the pipeline finishes, it generates a result back into our pull request, so we can track the behavior of our model. We have historical information about every pull request, and then we can, from here, deploy also the model. If we love Slack, most of us do, then we can get the same notification into email or into a Slack message. So as we develop, we can just see what happened in our training model directly in Slack, and everything is a hyperlink. So those hyperlinks will go back into the MLRun UI, where we can see all the different jobs and their behavior. So let's go to my GitOps project. Here you can see all the executions of each step. We can organize it by pipeline, by function, by job, and we can see all the variations, all the runs of every thing. Let's go into the training function. For example, you see that it automatically logged all the information about our training. It logged all the metadata, which workflow, which container, which pod was used on that for that workflow, all the matrix, even the code that was used for running this this training function could be viewed. I could just see this is the exact version of the code that I was running for this training function. I can see all the artifacts that were generated, each one of those. I can see the results because it's multiple experiments and I can actually compare. It chose this one because it has the best accuracy, but I can also go into individual results. I can even see the logs of my run, and that it's interactive. If my job keeps on running, I will see that progressing. It also monitors all the information about the artifacts. So let's go into artifacts. Let's take like a data set. I have a preview of my data set. I have a full analysis of my entire data set. I haven't written a single line of code in order to get all this full automation. Everything was done for me using wrappers and automation code. The other thing that we mentioned is that it also generated real-time functions. So this is using Nucleo, which is a very high-speed, high-performance serverless engine, very popular. So in Nucleo, which is also open source and runs over Kubernetes as a CRD, you can generate all those functions. Let's look into a function. This is a serving function. So I can see that this is a relatively simple function. It looks like KF serving, but it's much faster because it's using the Nucleo runtime, and it's much simpler because of all the unique capabilities of Nucleo. But it looks, if some of you have used the KF serving, the code itself inside the function is similar to KF serving. So very simple classes. Advantages of Nucleo, again, it controls resources dynamically, CPUs, GPUs, etc. It's stateful, it has many different capabilities. You can use triggering for HTTP, but also for like a dozen different streaming protocols. It does auto checkpointing, auto rebalancing. It's very advanced, very high performance serverless engine. So now here we had in our project, we had two different functions, V1 and V2. One thing that we need is a canary. So that, again, in Nucleo, not too difficult. You just go into the API gateway definition. You can set the authentication logic. You can set the routing logic. Let's just create a canary and give it. Okay, and here I can just set the canary and make it split the data between the two models that I generated. And I mean, from now, it's just going to be provisioned. If I want to monitor everything, that Nucleo also generates all the telemetry. Nucleo and MLRun generates all the telemetry into Prometheus, and you can also monitor it in Grafana. So again, you don't have to do anything for instrumentation. All the instrumentation, all the observability is built in for you. Okay, so with that, we've seen the demo, and I know there are a bunch of questions. So thank you everyone for listening, and I'm going to start going over the questions. Okay. So there is a question on setting up local development for the data scientist. So again, usually you don't use Argo, you just install Kubeflow, which is a set of tools. It's not a trivial task, but there are a bunch of documentation of how to set up Kubeflow. Once you've installed Kubeflow, installing MLRun is also relatively easy. There are many different full demos in MLRun of everything from churn prediction, predictive maintenance, image recognition, face recognition, etc., that you could just clone and use for your stuff. And with MLRun, there's also a lot of documentation, including also the aspects of installing the ecosystem around it. So like NFS for shared storage and Kubeflow and other things that you may need. So if you go into the MLRun documentation, you'll find it through the Git. You can just go and see all the details. There are also pre-baked images with like Jupyter and everything that you could use and just run a few Docker commands and start working. So that's on that answer and that question. Okay. Yeah, I haven't seen anyone wants to ask another question?
Yeah, I think that might be it. Yaron, is there a place where people can contact you after this webinar, like maybe a Slack link, or I think you might have had that in your slide deck. If you want to go back to that, we can show that for folks. They have any questions after the webinar?
The easier way for CNCF folks is to just find me in the CNCF Slack.
Oh, awesome.
You can also just connect through LinkedIn to me, and I'm pretty open. I'll approve you, and we can have a nice chat. And again, I'm willing to help any of you that is working on this, sort of trying to operationalize their effort. Sort of evangelism. You don't have to use our platform. You don't have to use our open source projects, but I think we do have this agenda of promoting MLOps and all this automation and Kubernetes as the mainstream platform for data engineering and data science.
Awesome. Well, we're getting a lot of comments in the chat that people really liked your presentation. I'd agree. Thanks again for a great presentation today. Thanks, folks, for joining us for today's CNCF webinar. A reminder that the recording and slides are going to be posted later today on the CNCF webinars page. That's cncf.io/webinars. Thanks again from all of us. I hope everyone has a great day and stay safe. Thanks all.
Thank you, everyone.